Okay, folks, welcome back. Section 10.5, Graphs of Trig Functions, Part 2B, second video. We've already done the front side. It's time to go to the back side. So we'll get started here. For each example below, determine the period, phase shift, stretch factor, and vertical shift for each function. Then graph each function on your calculator. Inspect each function so that you can see how the period, phase shift, stretch factor, and vertical shift affect each graph. Now, I am not going to graph each one of these, but I will graph a couple and show you. And then there's a note here. It says, hey, TI Inspire users, ask Mr. Vast to show you how to change the x-axis to a pi scale. So I will show you how to do that. You can also do it on the TI-84 platform. It's just not as convenient and visually helpful as it is on the TI Inspire. Okay, let's get started with the first problem here. What I'm going to do is, for this one, I'm just going to write at the top of the page that transformation form of the secant function. Y equals stretch factor times the secant of omega x plus phi plus our vertical shift. Folks, that's a B, not a beta. Okay. So we'll take a look at this this first example and go from there. So my A value here is 1. My omega value is 1. My phi value is negative pi. And my B value is 0. How does that turn into period, phase shift, stretch factor, and vertical shift? Well, from the front side, you should remember that the period of the secant function is 2 pi over omega. So if I have 2 pi over 1, that gives me a period of 2 pi. It takes a length of 2 pi on the x-axis for this function to go through one period. And I guess I should make mention of this. How did I find the values of A, omega, phi, and B? Well, A is the coefficient out in front of the secant function, and there's nothing there, so that's an implied 1. Same thing with omega out in front of x, that is a 1. If the form of my function is plus phi, that means phi equals negative pi, and then I have plus 0, so B equals 0. Phase shift is equal to the opposite of phi over omega. So that would be the opposite of negative pi. Make sure you can see that. The opposite of negative pi divided by omega, or just plain old pi. So phase shift of pi means that this graph will be shifted pi units to the right. Pi units to the right. Stretch factor, A equals 1, vertical shift is 0. Okay, so let's go see how this looks in our graphing calculator. I'm going to go ahead and add a graphs page and graph the secant of x minus pi. Grip it and rip it. And there's our graph. Okay, so I mentioned that I could change the x-axis to be units of pi, and it's more convenient when we're looking at trig graphs. So on a TI Inspire, I'm going to do that by going Menu, Window Zoom, Window Settings. And for x min and x max, I want to change those to increments of pi. So let's go negative 2 pi. To positive 2 pi. So I should see, if the period of this was 2 pi units, I should see 2 full periods. Auto scale will pick what the calculator will pick what it thinks is best. I like to kind of force this to be something that I would like, that's convenient for me, and I think we'll go with pi over 2. So each tick mark on the x-axis will be pi over 2 units apart. I'll go ahead and let y min and max stay the same. Grip it and rip it. There we go. So take a look here at pi over 2. We have a vertical asymptote. At 3 pi over 2, we have another vertical asymptote. You should compare this now with the graph of secant of x, and I'll go ahead and put that on the calculator screen right now. Secant x. So this is the parent graph of the secant function, and notice how the blue graph is shifted pi units to the right. That's the phase shift that we showed right here. Phase shift pi units to the right, therefore the graph secant of x minus pi is shifted pi units to the right. I am not going to go through this detail and show you each of these, the graph and then its parent on each of these functions, but I will do the first couple. Okay, so there you have example number 1. Let's move on to example number 2. This one looks to be more complicated. For this problem, I have an a value of 3. I have an omega value of 2. I have a phi value of pi over 2. And then I still have that vertical shift of 0. Okay, so let's go ahead and look. This one need to be careful because the period, if you recall from the first part of this video, the period for tangent and cotangent is not 2 pi over omega. It's just pi over omega. So in this case, my period is going to be pi over 2. Phase shift is still negative phi over omega. So that will be the opposite of pi over 2 divided by 2. And that gives me negative pi over 4 as my phase shift. So the graph of this function will be shifted to the left pi over 4 units from the parent graph of cotangent. Stretch factor in this one is 3. That's my a value, and we still have a vertical shift of 0. So let's go back to our TI Inspire and take a look at what this one shows up like on the graph. So for this graph, we have y, or f of x, equals 3 times the cotangent of 2x plus pi over 2. And then I have no vertical shift, so it's plus 0. Go ahead, grip it and rip it, and there's our graph. Okay, so let's kind of analyze this and see what's going on. I'll add the parent graph of cotangent up here so we can compare some of the features that we've discovered about period and phase shift. Folks, somebody just pulled in the driveway and the dogs are letting me know, so we're going to pause here for just a second. Okay, folks, false alarm. There's nothing to be concerned about there. Nothing to see here. Please disperse. Okay, back to the graph of this function. So there's 3 different things going on here. First of all, we have a stretch factor of 3, and that shows up in the graph because the blue graph gets steeper much quicker than the red graph. Notice how the red graph kind of curves down, and the blue graph is just more vertical, more straight. Okay, so that's one of the ways that this graph is different from the parent function. Another way is that our period, instead of it being pi units, it's pi over 2. So that means that this cotangent, the blue cotangent graph goes through one complete cycle in pi over 2 units. Notice the red graph, it takes pi units to go through one complete cycle. From x equals 0 to x equals pi is how long it takes for the red graph to go through one cycle. Last but not least, we have a phase shift of negative pi over 4. If we got rid of that phase shift, this blue graph would be shifted to the right pi over 4 units. So this point right here would show up here, and that would fit our full period into pi over 2 for the blue graph. Okay, folks, that's the last graph I'm going to show you on the calculator. For the rest of these example problems, I'm going to go through them quickly, talk about any highlights, and I do expect you to be able to graph these and identify how period, phase shift, stretch factor, and vertical shift appear in the graphs. Okay, back to the example problems. Number 3. y equals tangent of the opposite of x minus pi. Here we go. Okay, for this one I'm going to work to get it in the standard form of the transformation function of tangent. And I know that omega has to be positive. Right now it's a -1. So I'm going to change this to be tangent of the opposite of x plus pi. Basically, I factored out a -1 from -x minus pi. And then I'm going to use the odd function identity for tangent, which says the tangent of negative theta equals the negative tangent of theta. From here I can go to work on this function. Folks, there you have period, phase shift, stretch factor, and vertical shift for that function. Let's move over to number 4, 5 tangent of pi minus x, all minus 5. I'm going to do kind of the same starting point I did before. I need to get it in the standard form of the tangent transformation function, and I've already made a mistake. This should be minus right here. So if I switch this around so it's -x plus pi, then I factor out a negative sign, I'm going to get this. From there, I can factor out, I can get rid of this negative sign and write it here out in front of the 5. Okay, so we have -5 times tangent of x minus pi, all minus 5. We'll clean this up a little bit for you and then go to work. All right, folks, and there you have those 4 different descriptors of the graph of this example. 5 times pi minus x, 5 times the tangent of pi minus x, all minus 5. Let's go ahead and look at example 5 now. I'm going to move back into a cosecant function here, and this one's going to have a period of 2 pi over omega, because we're moving away from these 2 examples that involve tangent into cosecant. So here you go. Okay, folks, there's example 5 in its entirety. You might have some questions about what was going on up here. So I factored out a negative sign so that my omega was positive, and then cosecant is an odd function, so the cosecant of negative theta is the opposite of the cosecant of theta. So that's what flipped this -2/3 into a +2/3. Okay, now we're going to move on to example number 6. Okay, there's example 6, folks, and you'll notice I made a note here saying it's already in graphing form. That means I didn't have to factor out a negative sign or anything from inside the argument of the trig function like I did in some of the previous examples. Let's move on to, we got 2 more left here. Let's move on to number 7. All right, folks, here's example 7. I think you probably saw me highlight the period. This is pi over omega because it's cotangent function. Remember, cotangent and tangent have shorter periods than all the other 4 trig functions. The other thing I want to highlight for you here is, I don't know if I've talked about this, but you should be able to answer the question, what does it mean if the stretch factor is negative? Well, basically, that's a reflection across the x-axis. So you ought to be able to figure out from investigating a couple of these graphs in your calculator how that negative stretch factor reflects the graph across the x-axis. Okay, let's move on to this last example, number 8, and here we go. All right, folks, there you go with example 8 in its entirety. I did kind of move that trig part of this function down here to show you how secant of 3 pi over 2 minus 2t turns into the secant of 2t minus 3 pi over 2. And you'll notice here that I factored out a negative sign, and then it just kind of seemingly disappeared. Well, that's because secant is an even function, and the secant of negative theta is equal to the secant of theta. Same with cosine. So that's our even function identity. Anyway, that's it for section 10.5. I hope you've thoroughly enjoyed these videos and they've helped you learn some information about the graphs of trigonometric functions.